that has a typical number name that is FOV, that is field of view. You will see also in radar that when your resource is limited, if you increase your resolution, so you make your resolution bad, or you can make your FOV bigger that you want to see, and the opposite. Okay, so you cannot have a very good resolution and a very wide field of view because this goes into the number of pixels, and the number of pixels is limited. So the number of pixels, we see that is a sort of constant that is embedded in how do you do the system. For example, let us work now in the microwaves. This is a radar, this is a radiometer, it does not matter. So let us assume that your device is in this position and it is a long ranging. So the range is 10 kilometers. So you observe something that is, I don't know if I put 10 kilometers or 1 kilometer. I put 1 kilometer, okay? 1 kilometer distance, okay? And I want a resolution, so range, this is a range, maximum range at which you want to operate. And then you put your resolution. So ρ equal a 10 meters. This is called also geometric resolution. In this resolution we want to speak here. But today we see there are other measures of resolution. Resolution means that if at 1 kilometer there are two targets more distant than 10 meters, you want to see 2 points to different points. So there are two ways to satisfy this. The first is you use a real antenna. We see a real antenna as a particular case of the array. So the real antenna is practically a piece of metal, okay? And this piece of metal is L, is extent. Of course, is in the other direction. It's also a square, but we don't care because now I precise the resolution only on this plane, and this is X plane. For example, this is a radar for ships, another radar, and so for marine application you don't need the 2D, so you don't need a resolution in the other direction. And your antenna generates a beam that, different from a synthetic antenna, is always pointed orthogonal to the antenna. And you remember that the 3D beam, delta C 3 dB, is approximately lambda divided by L. Okay. This approximation is not exactly this number, but we use this. Okay. Now this means that if you want to have a very small resolution here, you need a very small angle, and you need to rotate your antenna in this position. So you rotate and you look here, then you rotate, then you rotate, then you rotate. So you need to operate the system with a sort of scanning. Always in remote sensing, you have a sort of scanning system that provide you the entire field of view. And let us assume that, for example, your field of view is a total angle of pi half. So the field of view you can measure in angle or in meter and so on. So let us say that you totally observe this entire field of view, and this entire field of view corresponds to pi half, and of course the size is pi half multiplied by 1000, so it's 3000 meters, 1700 meters. And first of all, when you consider this, you have to generate a very small antenna. So your angular resolution your angular width should be exact to get 10 meters, okay? You want 10 meters at 1 kilometer. So this angle is approximately this divided by this. So it's exactly, if this is a circle, it's exactly the piece of the arc, that is 10 meters, divided by the distance, that is 1 kilometer. This is 1 kilometer, remember, okay? And this is 0.01, is 10 milliradians, okay? Okay. 10 milliradians means that at 1 kilometer you get 10 meters. Of course, at 10 kilometer you get 100 of meter because it's an angular resolution. The resolution is always angular when you speak with antenna because the farther you go, the wider is the beam, and so the wider is the beam, the worse. Also with a laser, okay? 10 milliradians. Yes, do the check. No. 10 meter at 1 kilometer. Okay, 10 meter at 1 kilometer. This is rho, and this is R. Okay? Correct? Yeah. Okay. So the result was good. Okay. The point is that to get the complete scan of the field of view, you must move the antenna. So how many positions you have to scan? So how many beams? Well, in principle, any of this is a separate beam. Usually you won't overlap. But if you assume no overlap, so the number of beams should be, let us say, the minimum number of beams is the total area the total field of view that you want to scan. So the total field of view in this case is pi alpha, okay, radians, divided by your angular resolution, 0.01. Okay, so this is 177 beams. This is basically the number of freedom degrees, let us say, the number of resolution cells. When I say that the number of resolution cell, the number of pixel, well, pixel, if a pixel is a resolution cell, link the resolution between the field of view. I'm just writing this equation. Because if I want a better resolution, for example, I may acquire 1 meter resolution. 1 meter means 1 milliradians, and 1 milliradians I need 1,500 beams. 1,500 beams, I mean I take more time, 10 times what I take now to scan the entire field of view. So in the end, it's an order of time. So if you better resolution, you want more time. But time is a very critical resource because the lower the time, the lower the energy. So we need also to compute the energy. You should get enough energy to have an image. And so the energy goes to our source and goes to Boltzmann, to the black body, and goes to Planck law, and also Boltzmann if you want to compute. So we can ask, for example, when you use this equation, you remember, we were considering, we were deriving this last week just by assuming a far field. So your point is very far from the antenna. So we can ask, for example, are we in the far field? So does our approximation work? Because if you are in a near field, so the antenna is here, and you are here, you cannot expect the resolution to be lower than this number, of course. So your resolution should be, the far field tells that your resolution should be much larger than the aperture of the antenna, otherwise your resolution is L, of course. Here you cannot generate a focused beam at this length. So your resolution is this one, okay? This is the resolution that you consider at a distance R, okay? And this is L. This resolution here, of course, should be bigger than L. should be really small because you want, but you want it to be bigger than that. And in this case, we design the system to have the resolution of 10 meters, and we may ask what is the length of antenna. The length of antenna we get here immediately because lambda divided by L is the resolution, is 0.01 in this case. That is the delta psi 3 dB. In this case, I didn't put lambda, what we use. Well, let us suppose it is a microwave, so let us suppose lambda equals 1 centimeter. 1 centimeter is a 30 gigahertz system. 30 gigahertz used, for example, for automotive application. It's not so easy. At 1 kilometer it's good. It's not so easy to go far at 30 gigahertz because you have attenuation to the cloud, to the fog, and so on. But up to 1 kilometer, the attenuation is not so big. So 1 centimeter is safe. So if lambda is 1 centimeter, the length of antenna is 0.01 divided by 0.01, and that is 1 meter. Okay? Your resolution is 10 meter. 10 meter is much bigger than 1 meter. So, of course, this means that your resolution here is 10 meters. That is a good number, but much smaller, much bigger than the antenna. The antenna is just. So, when you go to the far field, so the field will be this, and when you go very far, you have the field that is distributed as this. This is how you expect the field to be going from near to far. So to far you see only, let us say, a beam whose width is this. Okay. And this is it. Okay. Now we have find the way to do the system with a real antenna. Okay. Now we can say what we can do if instead of using a real antenna, we use a synthetic antenna. So we use an array, just as we discussed the last lesson. So let us assume a second case, the numbers are always there, in which we have a synthetic antenna, cioè an array, an antenna array. The antenna array is a much better configuration because we don't need to make any rotation. Or let us say, you remember, if we want to have a beam looking in that direction, okay, we just need to make some coefficient here in order to have a proper phase. Approximately, if I draw the orthogonal, so this is the wavefront. So this field is, for example, two wavefront. I put it at lambda difference. I have to put a corresponding lambda x. I was copying the x-axis there. So if I design the weight in order that this is a sinusoid, I just excite a plane wave that goes in this direction. So I make a signal that is very directive, but in this direction. Okay? If I want to move the pointing in another direction, I change the coefficient. So this is very simple to do simultaneously. I mean, I make a different frequency, so by changing all the frequency, I can, so I excite this antenna, or if I receive, I just getting the other, I receive this antenna with different frequency, and simultaneously I can receive this position, and this position. So, for example, if I wanted to look at what is this direction, the gain in this direction, I take all this number and I sum together. If you take all this number and you sum together, you just use the antenna as is a classical way, as if it is a fixed antenna. But if you have to rotate, you take this number and you have to put different coefficients. So you take the same set of number and you put a second set of coefficients, and then you steer the beam in this direction. The point is that when you put this number, steering the beam here is just a combination, and steering the beam in another direction is another combination. So you can feed the same signal received by the same antenna by different combiner, different properly combined, and simultaneously you have the gain in this direction, and so on. And of course, with a narrow beam. Okay? So you can have multiple pointing simultaneously just by changing the way you, the coefficient you weight this signal and you sum. So here, for example, you have the pointing at T0 equals to 0. So the point is that how can you design now the antenna? In order to design your antenna, you must start from the resolution. So the resolution. Yes.
Sorry, I didn't understand what we are going to change in the array.
In the array,
Yes.
in the array, here nothing. Here this you are assigning the signal. Then you remember, I can delete here. You remember that in order to estimate, if you go in my lesson of last week, in order to estimate the field that comes from a particular angle, from a particular point that is located at angle psi0 and for all the time, you do an operation that is a linear superposition of all the antenna. So you remember that n was minus n plus n. Then you point here the signal received from all the antenna. So I put it the signal that depends on n is the position of the antenna and for all time. And I have to put here some coefficient. The coefficient is x of minus j to pi fx. That depends on the angle in which I want to point the antenna multiplied by x. Okay? This is, so what I say that I take the signal that comes from all the antenna. Here, for example, I have 5 antenna, -1, -0, 0, 1, 2. This is the value of n, okay? And depending on the direction that I want to estimate, I combine this value with different, you see, coefficient, okay? Actually, this is a Fourier transform. Okay, basically it's a Fourier transform. So this means that if I wanted to have the direction 0, I compute the Fourier transform at the frequency 0, because fx is sinus of c0 divided by lambda. Okay, so if I want to compute 0, I look at fx equals 0. So I put all this signal in a block that time by time provide Fourier transform, and the output of fx equals to 0 is the estimate of the signal here, estimated in c equals to 0 for all the time. Okay, you understand? If I wanted to look at the signal in another direction, I just change the value of fx. So in general, the Fourier transform gave me the component at a particular fx. But the Fourier transform actually do this operation. Okay? And this operation is just a steering of the array. Since the Fourier transform provides this result for many frequencies, so first, second, third, so usually as many frequencies as many samples you have, so you will have 5 frequencies. 5 frequency means that basically you divide all your direction in 5 values, and you have at frequency equal to 0, and then you have all the 5 frequencies. Okay, you have this frequency, this frequency, this frequency, this frequency. In our case, we are not interested to any frequency, because here, in this application, we are interested only on a limited angular sector. Okay? So we remember that the text was here you have your array, but you must combine your array within an interval that is my field of view, that is pi half. Okay? Then the point is that I want to compute the resolution. Of course, the resolution of this combination, if these are always constant, for example, I assume this constant and this is to be centered respect to 0, you remember that the resolution is approximately, so if it is constant, if you make the Fourier transform of a constant, okay, if you make the Fourier transform as a constant and you compute for different angle or different frequency, you say that your resolution, your main lobe, is approximately 1 divided by Lx. Lx is the dimension of the antenna. Lx is this number. Is exactly the physical dimension of the antenna. Is equals a 2n plus 1 multiplied by delta x. The total number of the antenna multiplied by every discussion with sheet. Okay, you remember? So the resolution is, let's say I want to call delta fx, it's a raw fx, it's a minimum frequency that is width, it's 1 divided by Lx. Okay, it's like you remember when you have an observation in a certain interval t, the resolution in frequency is the verse of the observation time. Okay, that is very simple. But now you don't want the resolution in frequency. You want the resolution in angle. Okay, so you just write that you just do, let us say, a sensitivity analysis in which you say that as for resolution you can write that delta fx, and then we will make a delta a very small value, is the derivation respect of psi of the relation that is this, okay? Sem psi divided by lambda, and this derivative you compute in a certain direction and then multiply by delta psi. Okay? So this means that a small variation delta fx is provided, this is cosinus of psi, and this is divided by lambda, is provided by cosinus of psi divided by lambda multiplied by delta psi. This is a sensitivity analysis. So a small variation in frequency creates a small variation in angle. Okay? So the point is that what is my, remember that this is the resolution. So what is my desired angular resolution? My desired angular resolution is rho phi, is the minimum phase variation, okay? And to get rho phi, I put delta fx divided by cosinus of psi multiplied by lambda. Okay? What is the minimum frequency resolution? Is 1 over Lx. So this is 1 over Lx cosinus of psi, psi is psi0, I put psi0, where you're pointing multiplied by lambda. Okay? So what I'm telling you is that if you have an antenna array, okay, and you wanted to look in this direction, okay, the resolution is similar to the resolution of a real antenna that has these sides. Why these sides? Because if Lx is this, okay, when you point in this direction, the orthogonal length is here, is Lx multiplied by cosinus of psi. Okay. So the resolution is always proportional to the sides of the equivalent antenna orthogonal to the view angle. It means that if you have this antenna, it's not very effective when you go here, when you look here. In fact, remember our ears are placed in this position. When the signal moves here, I'm very sensitive to very small variation of sound, but when the signal moves in the angle there, I don't have a sensitivity on the location of the signal. Why? Because when I look in this position, your effectively antenna width is very, very small. So it's proportional because your resolution has to be a different sensitivity to the range. Your resolution comes to the fact that the distance here is much bigger than the distance here, and then you can distinguish very well in this direction. But when you are very far, the two distance comes to be variation of angle do not provide significant variation of distance. Here I have the variation of angle gives a maximum variation of distance. Here, variation of angle does not change too much the distance apart. So, if I use this, now to compute my antenna, I must tell this, well, this is always 100 of the degree, you remember, of radians, 0.0 radians. This was 0.1 centimeter, okay? The cosinus of C is 0.7 because C0 is pi 4, okay? It's half of pi half, so it's the worst case, it goes in direction. And of course, your resolution will be much better in this, okay? So in this case, Lx is a number that you want to calculate, to compute. So you find that Lx is, Lx, you bring it here, so you bring 0.1 lambda divided by 0.01, this you bring here. Here you have the cosinus that is 0.7, and this is your resolution, your angular resolution, I remember, 0.1, okay, 1 centimeter wavelength, okay, 1 centimeter wavelength, okay, 100 of radians desired resolution, and then when you do this, you find that it's 1.4 meter. So you remember, if you have the real antenna, you can have it with 1 meter, okay? But the point is that if you look here, now you rotate the real antenna. And when you rotate the antenna is always 1 meter orthogonal. If you have the array, since the array you don't move at all, you use this trick to do the simultaneous beam forming in all the direction. So you simultaneous point your antenna with a sort of a trick, but now your resolution is smaller, okay, so it is wider, and you must compensate it by making the antenna a little longer. That is 1.4 meters. That is not so much, so you get a lot. So how many, let us say, samples you get? So how many beam? Of course, the number of samples, resolution samples, that you compute out of the FFT is that here again, the total field of view. The field of view is pi half, okay, divided by the angular resolution, that is number. The number of independent samples, I put independent sample, is again, I was in 154, if I remember. It's the same as before, okay? So nothing changes, okay? But the point is that to make this real array, we find that the total size of the array is 1.4 meter. But how many antenna we know? How many elementary antenna we know? So we have to design the spacing of the array. So we know that we have put antenna within 1.4 meter extent, okay? But how many antenna? So what is the spacing of the array? Delta x, okay? Well, remember that each direction corresponded to a frequency, a spatial frequency. So, as for the sampling, okay, each direction is a frequency, okay? So, if you want to correctly observe a frequency, a sinusoid at a certain frequency, what is the sampling related to the frequency? So, how much the sampling should be? Suppose that you have a maximum spatial frequency. How much is the sampling? Shannon theory. Usually, the sampling should be lower or higher? The sampling space. Lower. The smaller, the better. So, it should be lower, what? If this is a maximum frequency, not the inverse of the maximum frequency, but okay, twice. Okay? Okay, now you can consider that the frequency is related to the angle by this. Okay? Then you consider two cases. One, that you say whatever will be a signal, the higher frequency is obviously this one. This one is when psi, remember that psi is this, so is the angle with respect of the coming of the signal with respect to the vertical. If psi is pi half, the sinus of psi pi half is 1, 1 divided by lambda is 1. So you can put it in this way, 1 lambda divided by 2, okay? So if you make the sampling lower than lambda half, you are always good, even if the signal comes from this angle, okay? But you can here make a better arrangement to say that you know that the maximum angle is this one, because the field of view is limited from plus minus pi 4, okay? So it's pi 4 here and pi 4 here. You remember the field of view is pi half, okay? In this case, if you know that you don't want to look above this angle, you compute the maximum frequency as fx max is the sinus of pi 4 divided by lambda, okay? That is again 0.7 divided by lambda. In which case, the maximum second is lambda half multiplied by 1.4. Okay? 1.4 is good because you get much less antenna. The spacing is larger and you get much less antenna than before. Exactly how many antenna you want? Well, lambda is 1 centimeter. Okay? So 1 centimeter is half centimeter. Half centimeter, 1.4 is 0.7 centimeter. Okay? 0.7 centimeter. So you need a lot of antenna. How many? Well, exactly how many antenna at 0.7 centimeter are in 1.4 meter. So the number of antenna, elementary antenna, is 140 centimeter divided by 0.7. Okay? This is approximately 200, approximately. Okay? Is 1,400 divided by 7, 200. Okay? Yes?
How do you find 0.7 centimeters? I missed it.
0.7?
Yeah.
This. The spacing between the two antennas. The spacing is just not 2 alias. Since a direction corresponds to a sinusoid, you understand here, okay? So if you look at any direction of arrival provide you a sinusoid, okay? Of course, the spacing should be dimensioned by the higher direction because it's a maximum frequency. So the maximum frequency that you find, this means that the signal coming from this direction provide you a spatial frequency on the array, okay? And the maximum spatial frequency you compute as the maximum angle. The frequency, you remember this relationship, okay? This relationship means that you make a psi and you look at the frequency is the sine of psi. Of course, up to pi half. Fx is the sinus of psi divided by lambda, okay? And in negative, you have the same. So this means that approximately when the angle changes slightly, the frequency that you see increases linearly. But up to a certain way, then the frequency does not change more because you have a solution. If the signal comes from there, then the frequency goes down. Okay, so this relation is correct then. But you assume that your signal is confined in this direction. This means that your frequency is limited in this range, minus pi 4, pi 4. So this is the total range of frequencies that you get. Then your sampling step should not to alias this frequency, should be less than inverse of this bandwidth, okay? And this is a number. If you go to the number of beam of antenna, the number of antenna is the total antenna divided by the spacing, that is 200. You observe that 200 is very similar in the order of the number of independent samples, okay? So, I mean, each of these antenna is actually resolving one sample. So, if you want to observe 200 samples, because here you have at 10 meter and at pi of 5 field of water, and you have 100 of radians between two beams, you have here 170 samples. And to get 170 samples, you need a combination of about 200 antenna. Okay? So the number of antenna is equal to the number of samples. Each antenna gives a pixel, and the advantage is that you can use the FFT to have all these samples simultaneously. So you don't have to steer the antenna, you just use an FFT and you have the full image. Okay? You understand this because I will not do another exercise about synthetic array, but real array, but this will be done in the future. Okay, this is correct. If you understand the problem, questions, okay? Well, we need to move to optics. So how this works out in optics? Well, you all know because you have your eyes and you have your camera in your smartphone. It works also in the same way. So if you want to have many observations, you want to have resolution. So you have a FOV, you have a field of view. So what we told, you have a field of view and you have a resolution. Okay? Then there is a number of pixels. I call it pixel, that is a sort of resolution cell. But usually pixels is not proper as a resolution cell. Why? Because you can take one image of 100 pixels and oversample the image, increases the number of pixels, but the quality of the image is always the same. So you can make the pixels smaller and smaller just by oversampling. That is a trick. This will not change your resolution. But let us suppose that your pixel is a resolution cell. Now, the field of view divided by the resolution is exactly the number of pixels. Then you can have a choice, or what you do with a laser that you scan, and you need to move the laser in 3D. In fact, you remember how works scanning in this way, okay? So you need a lot of time because you have your laser that is very, very small, and you need a lot of time, okay? Or you can use a lot of sensor, and then you scan simultaneously. This is the second case. It was the use of a lot of sensor. If you have one sensor, you have a time t. If you have n sensor, the time divided by the number of sensors. And this goes to energy because you don't have usually time, or you don't have time to wait because the world moves. So you want a capture, a world that is moving, not still images, but you want to move it. And so you wanted to go the energy. let us look at it works in optics. I know maybe one of you has already knowledge of optics, but I wanted to review by this remote sensing the basic. Well, the simple systems that you do in optics is a pinhole camera. The pinhole camera is a camera, okay, that is pinhole. Is the simple camera that you can do, is like, let us say, Google camera, that is a very simple one, in which you have a very small hole, this is a pinhole, there is actually the hole, and here you have the sensor. If you have here your picture, let us say a Christmas tree, we are not close to the Christmas tree, okay, then the ray coming from here will exactly go here. So if this Christmas tree is illuminated, for example, by the sun, or in this direction, or in this direction, does not matter, but the ray that comes here is backscattered and goes in this direction. But the point of the top of the Christmas tree, only the ray that passes in the center of the hole enter in the camera. And so the tree, actually this comes also for all the other rays. And if I am good to make the drawing, the tree is upside down, okay? And this is the point. But the point is not that is upside down, and the size is very different, because here you want to see an entire fob, you want that goes in the space where you have the sensor. You have the CCD, charged coupled devices, that then digitize the image. Of course, the camera is 2D, and so there is an entire metrical sensor, and there is also the scanning on the other direction. But the other direction is exactly as this one. So a target that is extent D in the real world becomes an extent D in the small world. So D usually is centimeter or millimeter, and this can be meter or can be kilometer, because it's a wide image that goes in the dimension of the sensor. And if you look at how it works, these are the same angle. So this is theta, and this is theta, okay? This is the distance between the pinhole, okay? And then you can write a relationship that is theta is actually D divided by R, okay? By computing on the left. Big D divided by the big distance. Well, let's assume the F is the size between the pinhole and the plane of the image. This is also not big D divided by big R. Okay, so you are not convinced. You were right. Theta is big D divided by big R, but it's also small d divided by R. Okay? Then this is important because this is a very simple relation that relate the size of the image of the sensor as the size of the true image of the camera multiplied by this ratio F divided by F. This is a magnification. Is how big the field of view or how small the field of view becomes in your camera. Of course, in the real case, this should be a very small number, because if D is 1 kilometer, this can be in 1 millimeter, for example. Depends on the field of view, of course. And this is a field of view. So you understand the pinhole camera? So you say, why we need lenses? Of course. The problem of the pinhole camera is that this is even better by a lens. It has no, for example, the problem of lenses, no error, it costs nothing, and so on. The problem is that you don't have a lot of energy, because you are just a pin, okay? Energy is time, okay? We will go to the time, so we will understand. But its energy, it's a very small, so you get the energy that you can get only in a very small pin. And if you assume that you have a very small pin and then you have an entire wall, now only the light that passes in the wall pin are now dispersed in the entire wall. So the energy is small, it's much better to put a lens. So if you have a lens, here I don't want to make a complex optical treatment, but in the ideal case, then the lens has a center point, okay? And it works in that way. Here you have the same way your target, and also you have the size, and also you have the distance. The distance goes to the central, the optical central of the lens. This is the optical center. So it happens that the lens has two properties, okay? One, okay, ray parallel, okay, to this direction, so to the axis of the lens, converge in the focus. So this means that you have any ray that is parallel to this, in my plane is parallel to the ground, also this ray, they all converge, they are diverged in a length, so even a ray that is in this direction, they all converge in a focus that is this, and this is a property of the length. This can be changed by moving the focus, okay? The second property is that ray directed in the center are not changed. This is the second property. So if a ray is directed exactly in the center, the ray is not changed. Okay? All the rays that goes in the center are not changed. All the ray parallel converge in the focus. All the rays that transverse center are not changed. This means that at some point you make an image here. You see here and here and here and here. Okay. You make an image of your pine or let us say your Christmas tree that is not so good as the other one, and also this you can get the same relationship. The property of the focus, well, you don't make the image exactly in the focus, but you make it exactly, you make very close to the focus. So I want to make a second representation in which I put only the element that it's important to me. Okay, this is the top of the tree. Okay, this goes to the focus, and then you make the image in this position. That is very close to the focus. Okay, that is the intersection between this and this one. Okay, let us say this one. This is the focus. Okay, and okay, this one. Okay, this is D. Okay, and then the focus. No, it does not work in that way. Convert in a focus. No. So, sorry. There are 2 points. One is the center of the length, okay, and one is the focus. Okay. Now it works. Okay. So just to make a scheme, this is the center of the length. So this point is the top of the tree. Okay, and this also, this is in parallel, is the top of the tree. Okay, this is the top of the tree. Okay, what is advantage? Now that the top of the tree get 2 rays. This one and this one actually get many rays. So it means that in forming the image, all the energy captured on the length of the length is useful. So it's not only a pinpoint, but you capture much more energy because it's all this aperture and it has the behavior of a pinpoint camera. So if you write here, you are very close to the focus. If you write the relationship, the focus is this. Okay? This distance you call r first. This distance you call r. Then you can write a relation for the length that is 1 point r divided 1 point r first is the inverse of the focus. This is the most important relation of it. And in this case, r is big, so it's a kilometer, and r first is usually centimeter. So this means that 1 over r, okay, is r is much bigger to r first. So 1 over r can be ignored, okay, because it's a very big number, this is a very small number, and so this is a very big. So you get just this relationship, that 1 over r first, this is basically the focus. So it's very simple. Then you can write the same relationship. So you have the same relationship as this. So that I can write here, d is d multiplied by f divided by f. Okay. R is, what is f divided by r? Well, d divided by r first is this angle, but this angle is also this angle. And how is this angle? This angle is d divided by r. Okay? So d divided by r is this angle, that is also this. And so d first is d divided by r, that is this angle, multiplied by f or r first, that is the same. Okay? Do you agree? So this means that with the length, you have obtained all you get with a pinpoint camera, but the advantage is that you have much more light because this point is a contribution of many rays, so much more energy. Okay? Of course, this, in the end, this relation define your field of view. Okay? But now the point is how many pixels you can have in the field of view. Okay? How many pixels? How you can compute the pixels? So this is the length, remember. So how you can compute the resolution of the system? So the resolution. So what I write for a coherent system in last lesson is the same in the length. So a length open, if you are in the far field and you have a length, then the resolution, the angular resolution, is always lambda divided by f. Okay? So it means that the resolution, the distance of the fog, as I see, this is not really the fog, this is a fog projected on the, let us say, the sides. This is a fog, let us say. This is the field of view, and this is the sides of your acquisition system. So it's the CCD, or let us say the sides of your image. Okay?
Sorry, I didn't get how you define and measure the field of view. So
this is usually a data. You don't you define because the people that makes it's you that you want to observe a scene, that you decide how much wide I want. You have the choice. You remember that this is the focus, okay? So if I have this field of view, this signal goes in this position, okay? If I use a smaller focus, and I get this signal, if a focus is long, this signal has a small sides on it. If the focus is small, this signal, okay, instead then converging, let us the focal distance is small, this signal goes here, and then you. If the focal distance is long, this signal converge in this. Okay? So the sides on the fob depend immediately by the focal length of the length. So you see the focal is this. Okay? If the focal is a very big number, a big D becomes a big small d. Okay? So this means that as your sensor size is limited, the fob size, that is basically d, is the max, that is the sensor, multiplied by r divided by f. R is the maximum length that you consider, and f is the focal length of the length. If you make the length with a big focal, you see that your size, your fob, is small. Okay? But remember that if your fob is small and you have the same number of resolution cell, what comes to the pixel? You have a better resolution or a worse resolution?
With the same fob.
Same? No, you reduce the fob. Same number of pixels. Same number of pixels, smaller extent. Better resolution. So if you increase the focus, you have a small field, but better resolution. Okay? But usually, for the camera, people don't want the resolution. You don't want to see only your nose with a lot of pixels. You want to see your selfie. So this means that you make the field of view very small and you want to see an entire person. So usually the focal in a smartphone is very, very small number. Whereas the focal in professional, if you want to see, for example, not a distortion, because eventually when a big scene becomes in a very small fob, you put a sort of distortion. So you don't want a distortion, then use a long focal. But this is for, let us say, for landscape, for example. So for persons, for portrait, for example. So let us make this is the resolution, okay? This is obviously the maximum delta psi, the minimum delta psi, and the minimum delta psi eventually is the pixel, because the raw that I get on the sensor is lambda divided by L multiplied by the focus. And here again, I got the number. If the focus is small or big, I get a different value of rho, okay? Divided by focus, no. Divided by, multiplied by L first, okay? So, let us make some example. As an example, I take the retina display. Okay, retina display is the retina camera. This was introduced by Apple with the iPhone 4. So we are at iPhone 8 or 9. I don't remember. 10. Okay.
They skipped 9.
They skipped the 9, so it's a trick. Like Windows 10. You don't have 10 Windows before Windows 10. But iPhone 4 introduced what it's called the retina display. So iPhone 4 say, I get the same resolution that you can observe with your, so let us analyze the iPhone 4 with your eyes. And how you make the resolution with your eyes? You put the eyes of many people, and then you provide at some distance, this distance was 30 centimeters, and then you provide some pattern that has some distance. And you see, your resolution is when you see different stripes, instead you see only a uniform color, okay? So you can resolve the stripe. And they discover that at 30 centimeters, what is called the maximum sensitivity, here you can resolve 300 ppi, that is pixel per inch. Well, 1 inch is 2.54 centimeter. So in 2.54 centimeter, at 30 centimeter distance, you can see 300 of line, Okay, so this is a very good resolution, but eventually you say, if you get this resolution, you get a retina display. It's not useful to have a better resolution because you make image that your eyes will not appreciate, because the resolution will be better than your eyes. So it's good to have some better improvement, but not so much. So the sensor of the iPhone was using a CCD. A CCD is a matrix. Of course, the image is made this way, so it depends on how you rotate that was approximately 4.5 millimeter multiplied by 3.4 millimeter. Okay, and the number of pixels on the sides was 3064. This is a number of elements. A CCD is an array of elements. Each element is sensible to the three colors of the light. Actually, are three set of the three colors. And in the other sides is 2448 pixels. Okay, this was iPhone 4, so if you multiply these two numbers, you got around 8 million pixels. So this is 8 megapixels. Now, 8 megapixel is a good camera, but you can usually have 20, for example. Of course, it's not necessary that the bigger the number of pixels is better, because it's clear that you have maybe a better resolution, but you have less energy, okay? So less energy, it means that you have a loss in another part, okay, of the buttons. Let us, for example, you need another number. You need how big is antenna, that is called the pupil of the iPhone is very small. So the antenna is 1.8 millimeter. The size of the antenna, 1.8 millimeter. It's very, 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 very small, and the focal is 4 centimeter, 4 millimeter. 4.1 millimeter is half centimeter. You want the focal to be small, even because you cannot make it big, because the iPhone is narrow. So if you have a narrow iPhone, you have a narrow focal. So you cannot have a very good resolution. But let us assume that you have. So is this a retina display? So if we put a target like here at 30 centimeter, okay, and then here we have the optical center of the antenna, and then at a distance of about 4.1 millimeter, you have the plane of the image. This is the image plane. Okay? Now you know that the image plane should be, in the highest case, 4.5 millimeter. Okay? So as this angle is this angle, if this is 30 and this is 4.1, this is 4.5, this is about 33 centimeter. Okay? If you make the proper proportion between this and this and this and this is 0.45, that is 10% more than 0.41, okay? And this you got the number. So if it is 33 centimeter and it is retina, you can compute the number of pixels that the eyes can solve. The number of pixels we call resolution cell of ocular. Resolution cell. And the number of pixels is 3.3 divided 2.54, and this is the number of inch, and then you multiply by 300. So an eye would resolve this number of pixels. The number of pixels is to make the computation is 4280. Okay? It means that the smallest pixel this is a pixel that is corresponded to a pixel that excites this element in. You have 4 to our eyes has 42.80 pixels in our retina, our resolution. In the case of the iPhone, in these sides you have 3.64 pixels. So it's not exactly the retina. So Steve Jobs was still alive when when he presented the retina, and they are very, very good. All the discussion of Steve Jobs are on the web, or the speech, or the introduction is very good in advertising. So I suggest you to look. And very easy to understand. You see, it's not exactly a retina, because the eye actually have more pixels than what you have with the CCD, but we are, let us say, very close to the value, or for sure we are very close with this phone that we have now, that has more than 8 megapixels. But we don't know if we get the resolution. So having the pixel is not having a resolution, because this length eventually project here a beam that may extend for more than 1 pixel. So if you have 1, 2, 3 pixels and the 3 pixels have the same illumination, then it's not useful to have many pixels. Many pixels means oversampling, but it's not a resolution. So to understand if this is really a retina resolution, you must compute what is the number of the resolution cell. And to the number of resolution cell, the length is this, the pupil length. So if you have this length, then the angular resolution is again lambda divided by 1.810 minus 3, because millimeter, lambda divided by L, and this is the angular resolution, okay? And what is this lambda divided by? Well, lambda is between 400 nanometer and 700 nanometer, okay? So you remember that the visible in lambda has an entire range in which the highest frequency, this corresponds approximately to the blue, the violet, lower wavelength, highest frequency. The lower frequency are very close to the red or the infrared, okay? So the resolution, of course, you must compute in the worst case, okay? So the resolution at blue, it will be always much better as a resolution in red. So if we compare it with 0.7, 10 minus 6 divided 1.8, 10 minus 3, in milliradians you get something that is 10 minus 3, okay? Well, it's not exactly this. You have to multiply by 1.2, okay? Because 1.10 lambda divided by L was the resolution of a rectangular aperture, okay? When you have a circular aperture and you get the diffraction, then the relationship is very close to this, but you have to multiply by 1.2. This is due to the fact that you don't have a square aperture as we were considering in the past, but it's the diffraction of a circular aperture. Then, when you compute this resolution, you get 0.5 milliradians. Well, I remember that in the previous example, in the microwave, we have 1 meter of antenna, 1 meter, and this was going to 10 milliradians, okay? Here we have just 1 millimeter, 1.8 millimeter of length, and we have, so 1.8, 1,000 smaller with respect to the 1 meter, and still we have a resolution that is 100 better. So it's clear that the resolution in optics, everything is small. In microwave, everything is big, okay? But the advantage is that in optical you have no penetration. You cannot go through the cloud, you cannot go to the forest, you cannot go through a wall, and in radar you do have penetration. So you pay penetration, big wavelength with big devices, but this gives you one of the many advantages. Well, if you consider this, and then we consider a resolution cell on the image, that is 0.5 milliradians multiplied by the focal length, that is 0.5 10 minus 3 multiplied by 4.1 10 minus 3, that is a focal, and this is approximately 2 10 minus 6, is 2 micron, okay? In 2 micron length, in 4.5 millimeter, in 2 micron, you have approximately 2000 resolution cell. 4 divided by 2 is 2.2. 2.2 thousand resolution cell. So you have approximately in the image. And 2.2 thousand resolution cell is good with the number of pixels. You see, you have more pixels than resolution cell. And that is very good, because you must sample at least to have 1 pixel in the resolution cell. And so it's desired to have more. So let us say that the number of pixels in the CCD is well dimensioned with respect to the resolution that you get with the pupil. Okay? If you increase the pupil, you have a better resolution, then you need to put more pixels in the resolution cell. So the new iPhone have a bigger pupil and better resolution. Okay? And then you can compute, for example, the sides. Of course, you see the 3 centimeter are full, and this is the angle. So this is approximately the aperture that you can get. So the aperture is 4.5 meter, 4 meter, it's approximately 90 degrees. So you have approximately 90 degree aperture. Okay? If you want a smaller aperture, big focal length, bigger aperture, small focal length. But this 90 degree is a good aperture even for a self. Okay? So now we needed to make the evaluation by computing the energy. Okay? So how come about the energy? So for the energy, of course, we don't compute the energy in the light, but we do compute the energy when we don't have so much sunlight, for example. So let us say that we have a tungsten case, where we can do. So it's an evaluation that put all together. So for resolution and FOV, we understand this one, the FOV divided by the resolution is the number of pixels. Clear? Okay? FOV divided by resolution, number of pixels. Here you have so many sensors that you observe this one image immediately. In other systems, it's not done in this way. So let us make the example of how much energy then we get. So assume that we have the tungsten lamp. The tungsten bulb is the one that are no you will not see in the future because they are replaced by LED, and this illuminate a piece of your object. The object reflects the light, and it is observed by your, let us say, camera. This is your iPhone. So, how much energy I can get? Well, first of all, I can write as this is a black body, okay? So I get how much illumination I get from the lamp to the object, okay? Let us assume as a black body to be the bulb. So the radiance that we can get is the power of the lamp divided by, we use all in wavelength, this power spectrum, delta lambda, multiplied by the area of the black body. This is our black body, that is the length. Okay, and this is Planck. So by Planck, we know that this is 2 pi h square h c square divided by lambda 5 power multiplied by 1 divided by the exponential of h C divided by lambda Kt minus 1. Okay? This is the first relation. You remember the first we wrote. Basically, this tells you, provide me the temperature, okay, and this depends on the temperature, this curve, and I provide you how much power I get at a certain lambda. Okay? Of course, this is not like the sun. You know, the sun has a lot of energy, and the visible is near the peak. For a lamp, the visible is at the peak is not as visible because it's much lower frequency, much lower frequency. This is not lambda, this is frequency. Okay. No, it's lambda. It's correct. This is lambda. Much lower frequency means bigger lambda. Okay. So we can put the number. All these numbers are constant. The only term that is not constant is actually the temperature. So we put the temperature of the bulb to be 2000 to 2100 Kelvin. And what we get is, well, LPB is computed in this way, is a power spectrum. So I will find it in watt divided by meter, that is wavelength interval, divided by square meter. Okay. Instead, I want to compute LPB. I multiply by 10.9. This is usual to scale by 10.9 because 10.9 is the scaling factor that allows you to express it in terms of watt divided by nanometer of wavelength divided by 1 nanometer is 10 minus 9 micrometer, of course. But this is not the signal that you can get from the lamp. Why? It is not. It is not because this is a signal that goes here. Okay? And to compute the total power, you see here you have the black body. Then if you put this LBB, so this number, this equation, so you put LBB, that is that equation, okay? You multiply by 10 minus 9 so that you get in this unit. So this is only a change of unit, okay? And then you must say, in order to solve this, I compute it for the area of the black body. The area of the black body is the area of the filament of the tungsten. Suppose that I have 1 centimeter, I already made this example. By 1 centimeter, the ABB is 10 minus 2 multiplied by 10 minus 3 is 10 minus 5 square meter. Okay? So I take LBB, I multiply by the area 10 minus 5, and I got the power divided by wavelength for an elementary, a single element. Okay? The power divided by a wavelength. Sorry, I want to. It's this one. I want to be sure that I'm right. Okay. Not enough. I wanted to compute. This is power divided by delta lambda. But this is the power divided by delta lambda produced by the bulb. It's not the power that goes here, okay? It's the total power divided by wavelength, okay? Then to compute the power per surface here, I must divide the total power, so I put LBB 10 minus 9, 10 minus 4, that is 10, 4, and then I must divide by the surface at the distance. Suppose that the distance is 10 meters, okay? The entire surface at 10 meters is the entire surface of the 10 meter sphere. 4 pi 100. Okay? This is dimensional, it's a power divided by area orthogonal to the BB divided by unitary lambda. And this number, power divided by area and so on, is depends on the frequency. Okay? For this reason. Of course, if you have the smaller wavelengths, you have smaller power. Higher wavelengths, you have higher power. So you can compute from 400 nanometer up to 700 nanometer. So from the blue to the yellow. So you have more energy at the infrared. That is why when you look at the lamp, if you make a photo, the photo seems to be red than blue, because you don't have so blue illumination. And so when you have a photo, usually the camera do a compensation for the light. It's sort of called white balancing. What is white balancing? Since they know that there is much less energy at the blue with respect to the red, he says, they find me a white object and they try to change let us say, the energy, the mask per color in order to provide the image white, the white part of the image to be white. Usually this is done automatically, but if you don't do any compensation, you will see much more a red image. On the sun, this does not work because on the sun here is a top. So at 5700, the red and the blue are more or less the same amplitude. This is very different. So if you compute it at 400 nanometers, the energy per nanometer and per square meter is 1.8 10 minus 4 watt per meter, okay? 10 minus 4, so less than 1 milliwatt per meter. And if you compute it at the 700 nanometer, you have much power, so you have 0.007 watt per meter. So it's much power because this is less than 1/10 of a milliwatt, and this is 1.7 milliwatt per meter, per square meter. So 1 square meter gives you a milliwatt. So it's really a small power. If you see in the light, this number, if you use the sun, this number is 0.06, okay? So in the sun you get, let us say, 60 times 0.6. No, 600 the time the energy that you get by a lamp. So the sun is 600 the energy you get by the lamp. Okay? 600. It means that if you wanted to quantize, for example, the data, because you see how many pixels, how many, let us say, bit I should use. Well, remember that the dynamic in, let us say, blue light generated by this is a power, is 1.8 10 minus 4. It's blue tungsten. And in the sun, this is 0.06. So the ratio is the ratio of how much energy you can get by a sensor when you are completely in tungsten and completely in the sun. And this is 610 minus 2 divided by 1.8 10 minus 4. Okay? 610 minus 4. So this is 100 multiplied, it's about 500. Okay, so 500 means that if you wanted to quantize the system, you need at least, let us say, 9 bits. Okay, to have a good representation of a tungsten, and this is not a small tungsten light, because this is 2000 Kelvin, it's 100 watts, for example, you can compute by this relationship. Then the point is, well, we have already found how many bits we need, so the system, the sensor should be, dynamic range should be very wide. Now we can compute the total energy. So the total energy that we derive is this. We can fix worst case, best case. Okay, let us assume worst case. So the total power is this number. Remember that is watt per square meter per unit of let us say wavelength, and then we must multiply by a delta lambda. Let us say that we can put 20 nanometers. This is a single color. So this depends upon, as this is a power spectrum density, then you must compute how much energy you have in a color. Otherwise, if you make the integration over a wide range, you don't see the color. Okay? So this means that the more the number of color you want to observe, the smaller is this value. So more color, less energy. Okay? Because you must observe only, in order to filter this color, you must have a bandwidth filter. This is what our eyes is. In fact, it happens that when you look at an image that is very, very dark, you immediately don't perceive the difference of color, because when the image is very dark, you integrate over a wide area, and the image becomes closer to have 2 or 3 colors, so becomes very close to the color. So this is the number of color, but the way this number does not go so bad, and then I must multiply by the surface I'm interested. So what is the surface I'm interested? Well, this is a reflecting of the wall, and then I observe from my iPhone. Okay, my iPhone, we remember it was 0.5 milliradians. Okay, the angular aperture. So what is the surface that correspond, for example, if I look at a 10-meter distance? At a 10-meter distance, my diameter is D is 5 centimeter. Okay, 5 millimeter. 0.5 milliradians, if I remember this is a minimum angle that I can create, so it's a better resolution. This is 5 millimeter. So 5 millimeter at a 10 meter, it's a very good resolution. And this is much better with our phone. Now, well, if you want to multiply the surface is pi d square divided by 4. And d square is this number, is 5 millimeter. Okay? It's enough because I multiply the power divided by area divided by lambda, multiply by let us say the extent of a color, and so I get the total power in that color, and I multiply by the hour. This is a power that you get in watt. Okay, and actually you get 1.7 microwatt. Okay. Of course, if you increase the resolution, so if you make this spot smaller, you reduce this power. If you make the color resolution smaller, so you want to see more color, you reduce this power. So you say, why I need to get more color than what I see? Because, for example, you're not doing observation to have a picture, you're doing observation to measures. Sometimes you need a very high color resolution because you want to distinguish, for example, the fluorescence due to chlorophyll to other effects. So you want to do measure with systems that are more refined than eyes. So we'll see, for example, that you want also to do measure over a wide range. So also in the infrared, but it happens in the infrared, it's better in this case, but it's worse for the sun, because the sun has not a lot of energy in the infrared. Well, I remember I forgot to put an attenuation that is the reflectivity. So this is already considering a 0-3 reflectivity, because here, in order to compute the power, I think that not all the power that get to the surface is put back on you, because it's not a white body, but this is a partial white body, a gray body. I put a factor of 3, says that only 30% of the power goes in your direction. That is, let's say, an average good power. Then, if you want to understand how does this power relate to my measure, okay, it's very simple, because power is time. So, if you multiply power by observation time, okay, then you have the total energy. Okay? And you know that the total energy is quantized, because the energy, you remember first lesson, is quantized in photon. So this is the number of photons, okay, multiplied by the energy of a single photon. The energy of a single photon, you remember, it's a famous Planck relationship, is HF. So it is H multiplied C divided by lambda. Here again, depend on the frequency of the photon. And of course, the frequency of the photon, they are energetic photon, because lambda is, I was considering here the 700, the 400 micron, in this case. So you put here 400 micrometer, 400 nanometer, okay? And then, this is a fixed number. This is a fixed number, because h, c, lambda are all constant, lambda is a number. So I can get this relationship. I put the observation time divided by the number of photons, okay? And this comes to be a number that is this hc divided by lambda divided by the total power, okay? I want this big or small?
Small.
Usually you want a small observation time and a lot of photons, because they average. So if the quality, if you want to have a lot of picture and enough imaging, this you can put small. But you see that now the power goes down. So if you have a small power, this does not go to a very small number. Well, in this case, we are not put so bad. This is, in the bed is, I compute already this, and I get in, I already have this number. Okay, this is, well, depend on the wavelength, but is 1.610 minus 12. Okay. Well, what means 1.610 minus 12? Of course, this is an ideal case and so on. This means, because not all the power that you get on the sensor is converted into energy, only a small portion. So this number can go worse when you have losses due to not optimal system. So this means that at least you want one photon. Okay? Because with less than one photon you cannot do. And even one photon is not very good, because you see a grainy structure of the image. You want to see hundreds of photons. But in one photon, it means that you cannot have an observation time that is the order, let us say, of 2 picoseconds. Okay? Well, 2 picoseconds, you say it's a very small number, because if you want to make a feature, your object, your aperture can be 1 millisecond. But consider that now you are not using your camera for making a picture, but use your camera for measure distance. Okay? And this is that we need 2 picoseconds to get a number of photons. Well, if you wanted to use your camera to measure distance, you remember like a laser. So you measure, you measure the time of arrival, okay? Time of arrival, and then, okay, this is a delay, and then the distance, it's the delay multiplied by the speed. That in second by multiplying the speed meter per second. Okay? So, if I have a certain distance minimal delay that I need, and this minimum delay is 2 picoseconds, how much accurate I'm in measuring distance? Well, remember that the light make 300 micron, 300 meter in a microsecond. Okay, this means that make 300 micron in a picosecond. Okay, and in a couple of picoseconds, the light makes 600 micron. Okay, so it means that you have a couple of picoseconds. The accuracy in measuring distance is 0.6 millimeter. But if I use more, let us say, picosecond, 3 or 4, because I want more photon, maybe it goes 1 millimeter. And here you can see that the measure of distance that you get with a telelaser, for example, the Leica that you buy on Amazon, it costs 50 euros. The one of Leica costs 150 euros. Okay, the resolution is 1, 2, 3 millimeter. So you can get a resolution better 1 millimeter because you don't have the time resolution that you need to get enough photon. And this is written in the physics. So even if you are a good manufacturer, you cannot get better than this. We will see that in radar we can have accuracy that goes to the 1 micrometer. So that is why we use radar to monitor Marconi bridge. We can do it, of course. If it is enough to have 600 micrometers, you can use a laser, but it's a different technology. So we will see why the laser, and now we see why there is a link, and we will just exploit this. I had another example, but I will postpone it to the next lesson. That is all interesting and exciting. Okay?